say this is point A, B and C. Say we want to find out the displacement at point C. We're going to have to split this structure into two. A primary structure due to this point load and a secondary structure due to this reaction force. And then we draw bending moment diagrams for these and bending moment diagrams for the ones with virtual displacement, apply some formulas and find delta C. So let's draw the primary structure due to this point load. So we have a point load of 20 kilonewtons acting here. So the primary structure is going to look something like this. And here we have delta C in the y direction due to the point load P that does not equal to 0 because we see that there is a displacement. Now we're going to draw the real bending moment diagram due to this point load. So this is where it starts acting from. So this is how a bending moment diagram is going to look. And to find the maximum value of moment here, we have to do moment equals force of 20 kilonewtons times by the distance of 3 meters across which it's acting. So 20 kilonewtons times by 3 meters, we're going to have 60 kilonewton meters. Now, we need to draw the bending moment diagram this time. Here we drew the bending moment diagram due to the real one. So now we need to do due to the real curvature. K naught. So it's going to look the same, but we're going to have 60 over EI this time. So we're dividing by the flexural rigidity. And then we can draw the unit virtual force acting at point C, because this is where we want to find the displacement, deflection, at point C. This is a fixed end. So the bending moment diagram due to this one is going to start acting from here all the way here. And the value of the maximum moment is going to be the force of 1 times by the distance of 5. So we have 5. Also later on we're going to need to know what the moment is here. So where the point load acts. So basically at this distance 3. So here. And how do you find the moment here? The force of 1 times by the distance of 2. 1 times 2 means that the moment here is going to be 2. Let's just label this on for later. Nice. So now we want to find the deflection at C in the y direction due to the load P. We're going to start from here. We know that the external work is equal to the internal work. So the external work due to the point load is the virtual force applied times by the real displacement. Virtual force times real displacement. So external work is virtual force times real displacement. Remember that. And then the internal work due to the point load P, we have to integrate from A to B 1 over curvature, the real curvature, that's why we have this naught here, times by the virtual moment with respect to dz. Now, here we have virtual moment. We want to write the real curvature in terms of real moment. So, to make it like m naught m, v, d, z, here the curvature in terms of m naught, we have to take out this factor of ei as 1 over ei. We know this is a constant, so we're going to write it in front of the integral, 1 over ei. Now integrate the real moment, virtual moment with respect to dz. Now what do we integrate from? From a to b. So from here to here, so 3. So the distance from where the point load acts towards the fixed end of the beam. So we integrate from 0 to 3. Now, we have written the external moment and the internal moment. And now to find what we're looking for, we have to look at product integral tables and see before on our graph what two shapes we have forming due to the real moment. Let me undo that. And the virtual moment bending diagrams. So the force on the real moment diagram is a triangle. The shape. And the shape on the virtual moment diagram is like a trapezium. So let's draw this here. We have a triangle and a trapezium. And then you look on our product integral table and you see when you have one shape like this and one shape like this, the kind of formula we have to use in this case is going to be BL over 6A1 plus 2A2. Now what are each of these? L is the length for both of them. It's going to be the same value. B is the height of the triangle one. A1 is the shorter height on the trapezium, and A2 is the longer height on the trapezium. What are our actual values that we have to substitute now? The length we know is 3 because it's acting this way. Yeah? So from the load to the fixed support, to the, which is 3. Then we look at the triangle and we said the height is the B what we're looking for, but we're going to use this one. 60 over EI is B. 60 over EI. And then A1 and A2. We look at the trapezium one. A1 is the value of the shorter height, and we know the moment at this point is 2. We calculated it earlier. And the moment at this height here is 5. So A1 is 2 and A2 is 5. Let me show you one more time how we found A1 to be 2. So it's basically the moment here. Moment equals force times distance. The force is 1 times by the distance of 2. So 1 times 2, 2. So let's write this on. A1 is 2 and A2 is 5. Now we can find the deflection at C in the y direction due to P by substituting into this formula these values. So B is 60 over EI. Let's write the 6 on the denominator and the length as 3 multiplied on the numerator, so 60 times 3. Then we multiply by this bracket, A1 plus 2A2. So A1 is 2 plus 2A2, 2 times 5. And And when we simplify this, we have 180 over 6EI plus, multiplied by 12. So let me type this in. 180 times 12 divided by 6 is 360 over EI is the value of the deflection at C in the y direction due to P for the primary structure. Now we do the same thing but for the secondary structure. Here. So the secondary structure is due to this force. So we draw it acting here, the reaction force Cy. And the deflected shape is going to look something like this. Here we have the deflection at C in the y direction due to the reaction force, which we know cannot be equal to 0 because we're trying to find out what its value is. Then we draw the bending moment diagram for this reaction force. Trace down from where the force is acting, so here, and our bending moment diagram will look like this. The force is acting from below upwards. That's why your bending moment diagram is below the axis on the -1 instead of like this in the previous example of the primary structure. Now, the maximum moment at this point is the force times the distance. The force, which is the reaction force Cy, times by the distance of 5 because it acts along the distance of the whole beam. Now, let's find the one due to curvature. This one is R, and here we have K. It's going to look the same, but we just have to write it here as over EI. Now, just like before, we can draw a virtual force acting at C, because this is where we were trying to find the deflection. So this is where we applied the unit virtual force, dP equals 1. Fixed support at this end, and our bending moment diagram is going to look like this. The virtual bending moment diagram. The maximum value of moment here is going to be the force of 1 times by the distance of 5, so 5. But we will also need to find out the distance, the moment at this point here. Basically where the point load was acting in the whole diagram. And we trace it down, it would have acted here. So we want the bending moment value here. So moment equals force, which we know is 1 acting here, times by the distance until here, so 2. So 1 times 2, the value of the moment here for this distance is 2. We're going to do this later on. Now, let's do the same as before. We know that the internal moment, the external work is the same as the internal work because it's in equilibrium. And the external work due to the reaction force at C in the y direction is, just like before, the formula the virtual unit load, times by the real displacement at C in the y direction due to the reaction force at C in the y direction. So now to find the internal work, we have to integrate from A to C, this time across the whole beam, because our force that we are looking at is acting at the end, and you integrate from A to C the curvature multiplied by the virtual force with respect to dz. Now, like before, we take out this constant of AC from the curvature because we want it in terms of moment at the reaction force instead of curvature and reaction at. And we will integrate from 0 to 5, we said, across the whole length of the beam. Okay, so now we have the internal and external moments. But what we're actually looking for is the displacement at C in the y direction due to the reaction force at C in the y direction. And like before, we looked in the product integral tables to find what formula matches the two shapes that we have. Last time we had a trapezium because we were looking at the force that was acting basically here, which split it into a trapezium. But this time, the force that we're looking at is due to the reaction force, and this is acting at the end of the beam. So we're going to look at the end of the beam. So from the end of the beam all the way to the fixed support, we have a triangle. And the bending moment diagram due to the reaction force is also a triangle, but an upside down triangle, but still a triangle. So on the product integral table, you look for the two triangles instead of a trapezium and a triangle from last time.